Hi everyone and welcome back. So, we will continue our discussion on coagulation and flocculation process what we started in the last lecture. We did talk about the basic concepts of coagulation and flocculation, and in this particular class we will be discussing about the process selection and application, how basically the process is applied and how we select the coagulant. So, practically what we will be discussing is the selection of coagulant and what are the variety of coagulants available, the various organic and inorganic coagulants available in the market and their basic characteristics. Then we will be talking about the coagulant adds as well, what they are and what the role they might play in the coagulation process, and we will discuss the dosage estimation for the coagulant, how much dose must be provided and what impacts it may lead to the different systems, what are the criteria that should be followed, and we will also talk how experimentally we optimize the coagulant dose through jar test. So, to begin with, as we have been discussing coagulation and flocculation process, so essentially the process of coagulation and flocculation involves several steps. Okay. We must need to select a suitable coagulant, and then we must need to find the optimum dose of that coagulant. Okay. Of course, in addition we need to find the optimum operating conditions as well, and then we add that coagulant and do it in a flash mixture. So, we do rapid mixing in a flash mixture generally. Here what we mean is that we add the coagulant, whether organic coagulant or inorganic coagulant, we add that and rapidly mix that so that we can form a homogeneous solution of the coagulant. Then we do the slow mixing and allow the flocks formation. Okay, so, that is done in a flocculation basin, okay, or flocculation zone of a clariflocculator typically. So, we will do flocculation in this system here, and after that, so this is what basically coagulation and flocculation is all about, and after that we go for separation of flocks from the water, which could be done through filtration or through basically decanting the water. Okay. That means we go for a settling basis where the solids are settled and water is decanted from the top, or we go for flotation process where solids float from the water, solids float from the top and water remains in the tank. Okay. Or we just simply filter where solids are retained and water passes through the filter. But this process is in fact not a part of coagulation flocculation. This is essentially a filtration process or removal process. The coagulation flocculation part is this what we will be basically discussing, these particular steps. So, now when we go for a coagulation flocculation process, the first question that we face is what we are going to add. Okay. So, what coagulant we are going to select. Now, whatever coagulant we are going to select, it needs to fulfill some basic criteria. So, the basic characteristic that a coagulant must have is it should be non-toxic at a working dosage. We do not want to add a toxic chemical to water, because the water is going to be used for household purpose. So, we do not want any toxic, even if it is not going to say for household purpose, even if it is going to go for some commercial purpose or any other purpose, we do not want any toxic substance to add in the water. So, the one of the basic or very basic criteria is that the coagulant that we are choosing should be non-toxic. Then it should have a high charge density, which is helpful in coagulation process, and it should be insoluble in natural pH ranges, because eventually after adding the coagulant we want that to be removed from the water. So, it should remain in the solid phase so that it can remove through settling, simple settling process or filtration process. We do not want to add a substance which get dissolved in the water completely, and then the removal of the coagulant itself becomes a major challenge later on. So, these are the some of the key criteria which a coagulant should be following. Now, most commonly in water treatment facilities, and particularly the municipal water treatment facilities, the aluminum and iron salts are used as a coagulant. Okay. The common aluminum salts that are used are alum, then could be aluminum chloride. Alum, which is basically aluminum sulphate, could be used aluminum chloride, sodium aluminate, or polyaluminum chloride PAC, which is becoming more popular. Alum is by far the most popular coagulant in fact. Similarly, we have variety of option in the iron based coagulants, which are the ferric sulphate, ferrous sulphate, ferric chloride, ferric chloride sulphate. So, these are some of the iron based coagulant. There are other options also available. There are a series of organic coagulants, even polyelectrolytes and these kind of chemicals can also be used as a coagulant, though they are used as a coagulant adds also sometime. Then there are hydrated limes, there are magnesium carbonate and various other polymers, particularly the organic polymers are used as a coagulant. So, overall we have to make a choice between organic and inorganic coagulants. Both have their own advantages and disadvantages. The organic coagulant, the major advantage is they are very effective at treating higher turbidity raw water. So, when you have the very high turbidity to begin with, that means the colloidal concentrations or suspended material concentrations is high, then these kind of coagulant can very well treat that water. Okay. These are generally like polyamine kind of substances which works on a charge neutralization mostly. Okay. There are then melamine formaldehyde and tannins coagulate, which basically instead of coagulation they can also absorb organic materials such as oil and grease if they are present in the water. Okay. They are particularly well suited for kind of systems which is having higher turbidity, but if the turbidity of water is low to begin with, these coagulants are not going to be very effective there. Okay. So, that is the limitation of organic coagulant. Okay. They are good in treating high turbidity waters, but their performance is not that great when treating low turbidity water. That is where the inorganic coagulants come into the picture. They are more cost effective generally. Okay. So, they like the iron and alum salts are not that pricey. So, we can get them in a relatively cheaper cost. They are available easily and they are applicable for a broad variety of water and waste waters. Okay. They are particularly effective on treating raw water with low turbidity. When the turbidity is low, then also these kind of systems can lead substantially good performance. The advantage of alum is that it particularly kind of not causes the reddish brown staining of the floors, okay, which iron coagulant does like ferric sulphate. Okay. But the disadvantage side that it is only effective at certain pH ranges. It works over generally pH 4 to 8 range, pH 5 or 5.5 to 8 range, and we do not get a good flocculation with alum in some waters, whereas with ferric sulphate the coagulation is possible over a much wider pH range. It can work as low as pH 4. Okay, and flocks is formed are generally heavier than alum because iron is a heavier metal than alum. So, the flocks that are formed are heavy and they do not redissolve in water even at higher pH values, and the settling characteristic is also better. So, these are some of the like comparative advantages, disadvantages. If we see the common organic and inorganic coagulants, so like we have, as you say, that aluminum sulphate, which is also known as alum. This is a hydrated alum. This we may not have at all, or we may have 18H2O, 14H2O, variety of forms are available. Then sodium aluminate, aluminum chloride, polyaluminum chloride, which are PACs, then polyaluminum sulphate, PAS, then polyiron chloride, ferric chloride, ferrous sulphate. So, these are their molecular weights, these are their chemical formula. Okay. And some specific remark like the PAC, polyaluminum chlorides, used when the Hg contamination is a concern, generally it can be more helpful in that cases. Some of the popular organic coagulants are like DMA, DADMAC. So, these kind of structures or polymers may be used as a organic pollutant, organic coagulants. if we see the like inorganic coagulants which are more popularly, more commonly used in water treatment. So, their comparative advantages and disadvantages, like we discussed in fact these, the alum which is easy to handle and apply, most commonly used, it produces less sludge than lime and most effective in a range pH 6.5 to 7.5, whereas ferric chloride is very effective in pH between 4 to 11. Lime is generally used for pH control, but can also be used as a coagulant at time. For pH control it is very commonly used, okay, and it is very effective in that sense. Okay. The reaction is also pH dependent, it produced very large quantity of sludge. So, these are like example of lime, this is the ferric sulphate granules, this is the alum, and these are generally, all of these are available in various forms. Okay. So, like we may get in the crystal forms or granule forms, we may get in the powder form, we may get in the liquid forms, okay, and each form has its own advantages and disadvantages. Liquid is easier to apply because it is in a liquid and with a known concentration. So, when we are going to add in a water, we can compute how much volume is to be added and precisely we can add. Solids are that way, like needs more manual contact in loading, uploading, then mixing, producing, adding into the water. So, that would require more manual contact, which can be avoided with the liquids. Okay. Some other like sodium aluminate and PAC, these kind of things may have their own some advantages and disadvantages. Okay. PAC is used in some application, forks that are formed in more dense and faster. The amount of PAC required is also lower when we compare it with the other coagulant available, like other common alum or iron coagulant available. This is the common chemistry of some of the coagulants. Okay. So, what happens when we add say certain coagulant, like for say we are adding aluminum sulphate. So, it will react with the alkalinity present in the water. Okay. So, we have say sodium bicarbonate present in the water, it will react with that and form the aluminum hydroxide, which will actually form precipitate and settle, and then in addition it will form the sodium sulphate and carbon dioxide. If it is a hydrated say alum, like this is Al2SO4 whole thrice 18H2O, so hydrated alum, this also can react with the various forms of alkalinity, like calcium bicarbonate, okay, with lime, with sodium bicarbonate as in here, and it eventually will produce the aluminum hydroxide, which will form precipitate, okay, and that way practically we get these like this precipitate form, and they further help in the flocculation process. Okay. They provide precursor, and then particularly with the sweep floc formation they are very helpful, these kind of precipitates form. Okay. We may see like similar reactions from ferric sulphate or sodium aluminate kind of this thing, they also like ferric sulphate will also act with the alkalinity, will form ferric hydroxide. So, iron salts will form ferric hydroxide, aluminum salts will typically form aluminum hydroxide, and these are all precipitates. So, they will get removed from the system easily. Okay. Now, one of the interesting thing to note here in this, that in order for these substances, these coagulants that we are adding in water, in order for them to form precipitate, because of course the charge neutralization or the double layer suppression part they will do, they are going to increase the electrolyte concentration in the solution, and particularly iron and alum are so far used because of their higher electropositive potential. So, they are going to neutralize the electrolyte, they are going to kind of increase the electrolyte levels, and as a result they will do the charge neutralization part, double layer suppression part, which helps in bridging the existing colloid, but they themselves must be removed from the system. So, that is done through formation of hydroxides. So, either alum or either aluminum or iron hydroxides are formed. For them to react in water for forming their hydroxide, they need alkalinity in the water. So, there must be alkalinity present in the water. A requirement of alkalinity would be there when basically we are going to go for a coagulation flocculation process, and in some cases with low alkalinity water, when enough alkalinity is not present and we are adding a coagulant, we may need additional alkalinity, and generally in that cases lime is used as a source of alkalinity. So, we may additionally add lime or alkalinity in water at times, so that the coagulants that we are adding should later on be neutralized and should be basically forming precipitate. Okay. So, the level of alkalinity, control of the level of alkalinity is also very essential in the coagulation flocculation process. Now, that is about when we add a coagulant simply, but many times what happens in basically in quite a few waters, even if we add huge amount of coagulant, it fails to produce the sufficient or satisfactory level of removal of the colloids. Okay. So, the flocks will not be forming that great. Okay. Now, what to do in such cases? In such cases we may go for adding an additional compound which is normally referred as coagulant add. So, what happens, we add coagulant add, we use the coagulant add, and this eventually helps in creating the satisfactory level of coagulation over a much broader pH range. Okay. Now, the coagulant add generally are of two types. We may go for the insoluble particulate matters such as clay, sodium silicate, okay, or sometime precipitated calcium carbonate, then activated carbon might also be used. So, these are some of the common coagulant adds which may be used in the water in case of when we are planning a coagulation flocculation process. Okay. Now, they are used in the water which particularly have low concentration of particles, because what we are adding clay is also a form of kind of a colloid which will add on the colloid concentration in the water. Okay. Sodium silicate is also another form of clay itself. So, these are the some of the particles which will eventually add the turbidity in the water. Okay. Or we are adding the alkalinity, as just we were discussing that we may need alkalinity, or we are adding activated carbon which provides large surface area for precipitation of the particles. So, what essentially we are doing, we are providing either increasing the turbidity or increasing the alkalinity, or kind of providing the additional surface area, and all this helps in basically increasing the eventually the concentration of particle, because the coagulation may not be effective when there are very few nucleating sites, when there are very few colloids, when there are very few particles on which basically the further agglomeration can take place. So, we need chances of interaction, and for that we need significant amount of turbidity present in the raw water. So, if that is not there, then this kind of coagulants could be very effective. Okay. And these are all heavier particles, so their density is quite high, and when basically the flocks form, so the settling velocity of flocks will be increased because of the higher density of these particles, higher specific gravity of these particles, and even the removal of the flocks formed or agglomerates formed will also be enhanced when we add these kind of coagulant adds. The other type of coagulant adds which may be used, sometimes this is in fact known as the flocculant, okay, instead of just coagulant add. So, the other type of coagulant add can be like anionic polyacrylides kind of substances. Okay. So, these are the polymers in fact. Okay. We add the polymeric coagulant, and this which, as I told you, that this many people refer them as a flocculant as well. Okay. So, we can add these flocculants and this helps in bridging small flocks to agglomerate larger and denser flocks. Okay. So, the small flocks that are being formed when we add these kind of bridging elements, so those smaller flocks are bridged. Here we are not adding turbidity, but we are actually adding a flocculant as a form of the coagulant add. So, these are generally the polymeric substances, okay. And if let us say we are using alum or iron kind of salt, so they are basically because of their nature, because of their electropositivity. So, we generally go for the anionic polyacrylamides, okay, which has higher molecular weight of course, so that it can settle quickly, okay. In some time we go for non-ionic or even the cationic type of the polymers. They also have been kind of proven helpful or proven quite effective in some studies. We can go for the synthetic organics such as the anionic polyelectrolyte, okay, or we can go for the natural organics such as starch or its starch derivatives, protein, tannin, that kind of substance has also may be used as the coagulant add, okay. Now, we must ensure that the dose of the coagulant add that we are providing, they are carefully controlled, and we do not kind of want to have them a negative impact on the water quality. So, we tend to add these coagulant adds so that the coagulation process can be more effective, and we want that only, we do not want that they show some negative impact on the water quality. So, what typically happens under the there are 4 different zones of effectiveness if we look at a coagulation flocculation process. So, let us say we are having a system which is having different ranges of the colloid concentrations, okay. So, we have a chloride concentration ranging from S1 which is very low to S4 which is say substantially high colloid concentration, okay, and S2 and S3 are intermediate colloid concentration. Colloid concentrations are generally expressed in terms of surface area, because we get the measurement of the colloid is typically in the form of turbidity. So, how much light they are able to scatter, that will depend on how much surface area they are providing in the water for scattering of the light, okay. So, we do the measurement instead of just like gravimetric or in terms of mass, what is the total mass of the colloid, it is far easier to measure in terms of turbidity or in terms of the surface area of the colloids present in the unit volume of water. So, let us say there are different colloid concentrations, and we may see actually 4 different zones when we add these coagulants in the water. The different zones indicate different type of activities, okay. Like in zone 1, whichever case you take, in zone 1 when we add very low doses, okay, when we are adding low doses of the coagulant, okay, so the coagulant is insufficient to produce any sort of destabilization. So, in that case we will not see any sort of flocculation or any sort of removal there, as we are in zone 1, and zone 1 as we see initially whenever we are having, this is the coagulant doses. So, whenever we are having the low coagulant doses, we do not see any removal, okay. Removal or coagulation is shown here with the hashed lines. So, we do not see any removal in this case. Now, in the different cases we can see that zone 1 extends to the different labels, okay. Like in case of, if you see in case of when we have very low colloid concentration, this is all through zone 1. When we have increased colloid concentration, we have mostly like we have in the beginning we have zone 1, and then there is some formation of zone 2, and here there is again formation of zone 2, but after some time and with higher colloid concentration this is even further shifted. The zone 2 is the doses are sufficient to cause efficient and rapid destabilization. So, the zone 2 that we see here is when through charge neutralization or through double layer suppression, the colloids present in the water has been destabilized, okay. So, when they destabilize and any floc formation is taking place, that is happening in zone 2, this is purely due to destabilization, means as we add the coagulant, they are supposed to destabilize. Now, if you see here, when the chloride concentration is very low, we do not see any zone 2 here. That means the destabilization is not practically happening when with very low chloride concentration. destabilization, even if say destabilization might be happening, there is no removal. So, there is no flocculation, there is no flock formation, because even if say the charge neutralization has happened, but because the concentration of the colloids are very low, if you have say a setup like here and just 5 particles, so opportunity of these particles to meet and interact and form flocks is very small, because their density, their kind of concentration or their amount is very low in the system. Now, in zone when we add further coagulant, then we move to the zone 3, which is when the doses are high enough to cause restabilization. So, what happens that there are negatively charged particle, we are adding normally the cations. So, they first destabilize those, but there is a possibility, if we add too much, there is a possibility that the cationic charge particles are increased in the system, and as a result what we may see that there is again the particles becomes restabilized now, not because of the negative potential, but because of repulsion due to the positive potential they are carrying. Okay. So, then there is a possibility that we may, after this we may see a zone 3 coming in, where again it does not allow particle to bridge in. So, there is no removal even in the zone 3, and then the zone 4 is when we have very high doses which gets the sweep flock, okay, and that results in a good destabilization. So, when we add further coagulant, what we see that there is a large mass, as we discussed in the previous lecture also, there will be a large mass of the sludge will be produced because of the coagulant itself, like if we are adding alum or iron salts. So, the ferric hydroxides or aluminum hydroxides, they will be in a sufficient mass, and because of this sweep flock action, they will be actually removing the turbidity or coagulants present in. So, that sweep flock has nothing to do with the stabilization, not much to do with the stabilization or destabilization part, it is because that has created a substantial mass which is going to settle, and in the process it will remove the turbidity or the colloids present in, which are basically going to come in the path of that settling flock, settling large mass of the flock or settling large mass of the metal hydroxides what we have added. Okay, and then through entrapment or enmeshment, these also get enmeshed in the flock and get removed from the system. So, that is fourth type. This will happen only when we have very high coagulant doses, and as you can see that the fourth type, depending on what level of the colloid concentration we have, if we are working at very low colloid concentration as just we were discussing here. So, the possibility of removal through the just destabilization is not possible, it is generally removed only through the sweep flock formation. When we have a little more colloid concentration, some destabilization will occur, but again it is not good enough to kind of see the flock formation, and as a result again the major removal is possible through sweep flock formation only. When we are having significantly substantial concentration of the colloid, then we will see that it is first forming zone 1, then it is actually getting good removal due to the destabilization itself. However, if we add further, it will show the restabilization due to the charge reversal, and then if we further add, it will go to the zone 4, which is actually the sweep flock formation. If we are beginning with very high colloid concentration, the turbidity is very high, then we straight away, like when we add the sufficient doses, we will see we go into the zone 2, and the colloid concentration is so high that all whatever we are adding goes on to the neutralization part, and we in fact do not need to go to the sweep flock formation. Generally that is not seen, and even the zone 2 itself, because of very high mass of the colloids, we get large precipitates formed here itself, and we can get the removal through the destabilization itself. We do not need to go to the sweep flock formation level. So, what typically happens, like this is what will happen if we add basically colloid concentration and the coagulant doses. So, if we are at very low colloid concentrations, what we see is the removal is through only zone 4 sweep flock formation. If we are into somewhere into kind of zone 2, then or say S2, then what we see is we may see little of the destabilization process through charge neutralization, but again it is not probably sufficient enough. So, the major removal is again happens in the zone 4 through sweep flock formation. With higher chloride concentration in S3, we can actually get removal, substantial removal here itself, and then we may not need to go there, and in when concentration is further higher, we get this thing removed in the zone 2, sufficient level of removal in the zone 2. Okay. At very high, we generally do not get sweep flock because much of the coagulant is used by the colloids. Whatever coagulant we are adding mostly is getting used by the colloids. At level S2 and S3, there is sufficient colloid concentration for destabilization before we go for sweep flock formation. Okay. But if we are at lower S level, it is rather much easier to restabilize because this is the zone of destabilization over here. Now, so based on all this, we can guide on what doses must be selected or what kind of coagulation flocculation system must be selected. So, if we are at high colloid and low alkalinity levels, then we do not need to worry much about the pH, though lower pH is better, but it should not be very low, so that it causes the it increases the solubility. Okay. So, the destabilization is generally happen by the charge neutralization because the colloid concentration is very high. Okay. Generally, there is no concern of overdosing, as just we see it does not usually go to the sweep flock formation level because of the colloidal surface area present is substantially large. So, this is a easy case, okay, to deal with when we are having a high colloid concentration, but and high alkalinity. So, then the choices are to be destabilized by the adsorption or charge neutralization at kind of neutral pH, okay, or we add acid to lower the pH. Okay. So, because if there is too much of alkalinity, it is alkalinity is helpful in the sweep flock formation rather, okay, because it will produce the hydroxide. If you want to go for the charge neutralization, we need a lower alkalinity in the system because we do not want the coagulants that we are adding to react with the alkalinity. We want them to be present in the system in its ionic stage, so that they can help in the charge neutralization process or double layer separation process. So, for that purpose, so if you want to get removal in zone 2, we need low alkalinity. If you want to get removal in zone 4, we generally need a substantial amount of alkalinity present in the system. Now, here, so either we basically destabilize by the charge neutralization at neutral pH, or we add alkalinity to lower the pH, whatever we are choosing, like whichever is the most cost effective can be chosen. The third case, which is low colloid concentration and high alkalinity. So, for this case again, either we destabilize by high doses to give the sweep flock, or we can add a coagulant add such as say bentonite. Okay. Now, the coagulant add helps in kind of increasing the coagulant concentrations. Okay. So, we may go for two things in such cases. Okay. One is that, like if we just look at the previous graph over here. So, if our system is say somewhere here, okay, what dose of coagulant we need is in this range. So, this is basically minimum dose required. We need very high dose, or if say we are somewhere in this range, the doses needs are very high. If we add little of the clay, bentonite is say some form of clay or any kind of stable thing which will yield the turbidity, which will increase the turbidity of the system, which will increase the colloid concentration in the system. So, if we move from S1, if we say move from S1 to S3, then if we move to S3 we can achieve the coagulation at a much lower dose. So, instead of like here what we need is addition of this much of coagulant dose for say. Okay. So, we have two choice, either we add this much of coagulant dose. So, say this is the dose of coagulant DC, or we instead add only this much of coagulant dose and add this much of the clay. Okay. So, this is dose of the bentonite clay say dB, and then this is the say the dose of coagulant what we are using here. So, we need to see which one is the more cost effective, either this like we add little of clay and then get the coagulation at a lower doses, or we do not add clay and add high doses for sweep flock formation. So, we need to basically make a decision based on the cost, and these two options we will have. Okay. Like either we give high doses to give the sweep flock, or we can add coagulant add such as say bentonite to get the destabilization at lower doses. And then the last case, which is low colloid concentration and low alkalinity. So, this is generally the most effective case, this is the most difficult case in fact, and generally requires to add alkalinity or colloid again, like because we are having low colloid concentration. So, sweep flock formation is difficult, and we are having low alkalinity. So, sweep flock formation is difficult, and low chloride concentration. So, the neutralization is difficult. So, we are actually lacking on both the parts. So, either again we add enough alkalinity so that we go to the sweep flock formation level, or we add the clay or those kind of things so that we go for the kind of sweep flock formation. Okay. So, or if when we are adding clay we can get the destabilization at lower doses. So, either we add enough clay so that the colloid concentration increase and we can get it done, or we add the alkalinity and then add very high doses of very high doses or substantially high doses of coagulants so that sweep flock is formed. So, in any case we have to add something. Okay. Otherwise, this is a very difficult case to deal with. So, next is basically this is what we have been discussing is about the how we work out the different doses. But again these are all theoretical concepts that what dose we should keep. For practical purpose, the doses of the coagulant are estimated or rather optimized through a laboratory test which is known as the jar test. Okay. So, jar test is a simple laboratory procedure. We have a apparatus like this which is known as jar test apparatus. Okay. And this will typically have 6, may have sometime 4 to 6 beakers are generally there. Okay. And each will have a basically stirrer, okay, variable speed stirrer. So, this like we can achieve stirring at variable speed. Now, what is done typically, we fill all these beakers with raw water and keep one as a control. So, say this is our control, we are not going to add anything to this, and then in all other beakers we add variable doses of coagulant. So, let us say here we added 2 milligram per liter, here we added 4 milligram per liter, similarly 8 milligram per liter, 12 milligram per liter, 20 milligram per liter. That way we can add the different doses, and then after we added the coagulant here, we rapidly mix it maybe around 100 rpm or 80 rpm for a minute, or generally maybe a less than minute, but about a minute we can mix it, and then that is when the mixing is done. So, we assume that we added the coagulant and we rapidly mix it. So, our coagulant is well mixed in the system, and then what we do, we reduce the speed of these stirrers and we do it at a slower speed, usually 20 to 30 rpm range for flocculation purpose, and that we may go for 15 to 30 minutes. Of course, this is not a strict range, some people do it even at a lesser or higher times. So, during this period what we try to achieve is that the contact between the particles, so that the flocculation takes place, and after the time what we have decided, we stop the stirrer. So, the stirrers are completely stopped. okay, and we allow the content to settle for the desired time, which is usually 20 to 40 minutes, and then the optimum dose we can determine by the measured turbidity of the supernatant water. So, once the settling is happened, we can measure the turbidity of this. If we are not measuring turbidity, traditionally, like when turbidity measurements were not that easy, people used to just make a judgment based on the visual inspection. So, like visually also I can see, okay, if I see, say this is my control 0 dose, this is say 2 milligram, this is say 4 milligram, 6 milligram, 8 milligram, 10 milligram. So, now I can see that this is dirty, this is also not good, this is also not that good, and maybe these 3 look same. So, that means adding more is not going to help. So, I can choose maybe a 6 milligram per liter as a dose. So, some visual interpretation also used to work earlier, but nowadays we have better facility of measuring the turbidity. So, what can be done is based on the doses, and we may measure the turbidity and plot this. So, what we will see that at a particular dose, generally what we will see that at a particular dose we are actually getting the minimum turbidity. So, we select this as an optimum dose. Okay, many times we may get a curve like this, or many times we may get a curve like this, that means it is actually not increasing, but it is again constant. So, what we can choose, like from where there is no further decrease, that point we can choose. Okay. Similarly, the same type of jar test may be used for say optimizing other parameters like pH, mixing speed for flocculation, flocculant time. So, what happens, we keep all the parameters constant, like in these jars what we will do, we will make one control and in the other vary one parameter. So, for say if you are varying doses, so then we will ensure that all are at same pH, all are at mixed at the same speed, all are at allowed to be basically mixed for the same time. Now, similar exercise can be done, let us say instead of like what we are doing here, we decided that we are going to add say 6 milligram per liter. So, we add 6 milligram per liter doses in all and then vary pH. Okay. So, we are doing one at say 5 pH, one 5.5, 6, 6.5, 7, 7.5, okay, we are doing at variable pH, and then again we plot that which pH is giving you the least turbidity. So, we can select that pH. So, we can optimize similarly pH, we can optimize the mixing speed for flocculation. So, like some, not all, but some setups comes with where we can vary the speed of the different stirrers. So, let us say one we are mixing at a 15 rpm, then 20 rpm, 25 rpm, say 10, like, or maybe 10, 15, say 10 rpm, 15 rpm, 20 rpm, 25 rpm, 30 rpm, that way, and then again plot with the turbidity which one is giving the least. We can have the different times, okay, we can stop, let us say we are mixing all at same rpm, but then one we stop after 10 minutes, another we stop after 15 minutes, this we stop after 20 minutes, this we stopped after 25 minutes. Okay. So, that way we can see, we can do it at a variable flocculation time and see which one is giving us the best removal. So, like keeping all other parameter constant, this kind of setup provides us the opportunity to vary one parameter at a time and optimize that. So, that is about the using jar test and getting the optimum doses. The optimum dose estimation is very important, because if we are adding more, so like if you are going for the overdosing of the coagulant, then it increases the treatment cost first, because we are adding more compound, more chemical. It re-stabilizes the colloids, that possibility is again there. It will increase the sludge mass, because if you are adding more coagulant, it is eventually going to get converted to the sludge. So, the amount of solid waste generated or amount of sludge generated is going to go high, and it may have some public health concerns also if it is not adequately removed or recovered back from the system. If we are going for underdosing, then the major problem is that we will get lesser degree of removal, and as a result we will fail to meet the water quality target. So, we do not want to go this, because this is not fulfilling our purpose, At the same time, we do not want to go overdosing also, because that is also creating lot of problems. So, the best solution is that we optimize and choose an optimum dose. Okay. So, we choose an optimum dose depending on the system, and little play around is possible, as we discussed that we may need to add clay or add alkalinity at times, okay, so that we can get a good removal through these processes. So, we will conclude this lecture here, and in the next class we will be talking about the design and kind of operation and of these coagulation flocculation system, okay, how they are operated actually in the field, okay, what are their process controls, and how these can be designed. So, we will discuss that in the next class. Thank you for joining, and see you in the next class.